2.3, characterizations of invertible matrices. Theorem 8, the invertible matrix theorem. Let A be a square n by n matrix. The following statements are equivalent. For any given A, they are either all true or all false. So this should be for any given A. A is an invertible matrix. B, A is row equivalent to the identity matrix. C, A has n pivot positions. D, the equation AX equals 0 has only one trivial solution. E, the columns of A form a linearly independent set. F, the linear transformation vector A to AX is 1-to-1. G, the equation AX equals B has at least one solution for each B in Rn. H, the columns of A span Rn. I, the linear transformations X to AX maps Rn to Rn. J, there's an n by n matrix C such that CA equals I. K, there's an n by n matrix D such that AD equals I. And L, A transpose is an invertible matrix. Use the invertible matrix theorem to determine if A is invertible, where A equals 1, -4, 2, -3, 11, 7, and 0, 1, 3. So first, I have A, which equals 1, -4, 2, -3, 11, 7, 0, 1, 3. And I'm just going to go ahead and see if I can get this down to maybe one of those. It only has to be one of the characteristics of an invertible matrix. So there's many different things that you can do. So the first thing I'm going to do is I'm going to take 4 times row 1 plus row 2, or minus row 2. So I'm going to take 4 times row 1 minus row 2. So 4 times row 1 minus row 2. And that would give me 0, 1, -1, and my last row is going to stay the same. Then what I'm going to do is I'm going to take 2 times row 1 and, or -2 times row 1 and add it to row 3. So that gives me a pivot position there. And the last thing I'm going to do is I'm going to take -13 row 2 and add it to row 3. So here I have 3 pivot positions, so it is invertible. Because that equals my n. Invertible and linear transformations. For an invertible matrix A inverse AX equals X for all X in Rn, and A inverse AX equals X for all X in Rn. A linear transformation T, R to Rn, is said to be invertible if there exists a function S from Rn to Rn such that S of Tx, our transformation, equals X for all X, and T of S of X equals X for all X in Rn. Theorem 9. Let Rn to Rn be a linear transformation and let A be the standard matrix for T. Then T is invertible if and only if A is an invertible matrix. In that case, the linear transformation S given by S of X equals A inverse X is the unique function satisfying S of t of x equals x for all x in Rn, and t of s of x equals x in all x for all x in Rn. For this, assume t is invertible. T is a linear transformation from Rn to Rn. A is the standard matrix for t, and t of x equals a of x. Exists an S such that S of t of x equals x.